Hi everyone here and on Zoom there. Can you hear here on Zoom?
Yes.
Thank you, Gilang. Thank you. Yeah. So we have two cameras here. And you can see people on the Zoom can see the meeting room as well. Yeah, great. So it's working. Thank you. Okay, I think we'll get started here. Thank you everyone for coming. I am Xiangrong Kong. Are we seeing this? Okay, let me minimize this. This is better. Okay, so I am Xiangrong Kong. I am a biostatistician here at Wilmer Eye Institute. And I also have joint faculty appointments in the Department of Biostatistics, Epidemiology, and Health Behavioral Science in the School of Public Health across the street there. So here, within Wilmer, I'm very honored to be the director of the Wilmer Biostatistics Center that has long history, actually over 40 years of history now. And for my own research, I'm also the director and biostatistician for our large, for the coordinating center of a large clinical trial in retinitis pigmentosa. So hopefully with today's seminar, the purpose is really to provide some educational training resources on behalf of the Wilmer Biostatistics Center to the Wilmer community, and also to the NEC Attack clinical trial community. We might have some people from the clinical trial. The NEC Attack trial involves over 30 sites from the US and a few other countries there. So a little bit disclosure before we move on the slides here. This is 1 hour, very fundamental, foundational introduction talk about power and sample size calculation, this topic here. But this is actually, the slides are adapted from the course that I developed and teach in the School of Public Health on the topic of power and sample size calculation. The course is 1 credit online and offer multiple times throughout the year. It's open to the general public during the summer offering there. So having said that, let's look at the introductory topic on the whole topic here. So it is.
Are you recording this question?
Yes, it is recorded. Yeah, and by the way, yeah, this talk is being recorded, and we will post it on the Wilmer Biostatistics Center webpage later. Trying to advance the slides here. All right, so what we are going to cover is 2 sections. First is what is power and sample size calculation, or when we will need to use them. And here you'll see some motivating examples, and hopefully you'll see why we will need to use the calculation tool there. And then we'll move on to talk about how to do power and sample size calculation. And specifically, we will only focus on the simplest scenario, which is a 1 sample mean problem. But the idea is by going through this simple example, we'll review the concepts of statistical hypothesis testing framework and also the concept of power, p-value. These are all interrelated ideas there, and then see how to calculate the power. So here you're going to see the different elements that we will need in terms of doing power and sample size calculation there. So hopefully with today's talk, after this, hopefully you'll have a better understanding of the statistical hypothesis testing framework and have an accurate understanding of the concept of p-value and power and other related concepts like minimum detectable effect size there that we'll see later. And also to be able to recognize when you should do a power and sample size calculation there, especially when you're designing a study there, including the relevant pieces of information that you need to put together during the study design stage. And then with this 1 hour foundational talk, hopefully you are able to interpret PSS calculation results there. So the first part, let's look at this when we will need power and sample size calculation in general. And here we are going to see 3 motivating examples that are based on my own collaborations there. The first example is I was asked by a collaborator to help design a community randomized trial in Uganda, Rakai, Uganda. This is an African country. You can see the map here, right? Yeah. So this is an African country here, and Rakai is in a southern district of the country. The context is this fishing villages, as you can see. Even a few years ago, the public health crisis at the fishing villages was the HIV prevalence there. So HIV prevalence was as high as nearly 50%. Even that was a few years ago. I mean, imagine half of the villagers were HIV infected. So certainly that deserves public health attention and intervention there. Now the team was trying to do a clinical trial using using community health workers like this, and equipped with mobile health technologies like mobile phone and an app there. So the intervention is the mobile health, the community health workers will go to these villages and educate the villagers about the HIV prevention service programs available near them. These are widely proven to be effective in HIV prevention there. So here the question, of course, how big the study trial, the clinical trial need to be run there. Especially the how many villagers or how many homes that they need to go to educate the people to uptake on HIV prevention service programs there. So that was the calculation I needed to do. I mean, clearly that's a parent and sample size calculation problem there. Now moving to another very different example where I was not calculating sample size, but this was also a real study within Wilmer. That was a early phase clinical trial on albinism patients. Albinism, if you have heard of it, that is a genetic disease, and the genetic mutation causes something wrong about a pigmentation there. So the phenotypes including like hair, the hair color, skin color, and it could also have phenotype in the macula there, where their macula lacks certain pigmentation. So this clinical trial, the intervention was to test whether a dietary supplementation of lutein and zeaxanthin, by taking those, whether the patient's the macular pigment optical density could be improved there. So that was a clinical trial there. But this, I was not calculating sample size because this is actually a very, very rare disease. And the investigator decided that based on the catchment area, which is near the mid and to the east coast of the United States, and also within a year also of enrollment period, at most they can find about 20 such patients there. And because this is a relatively safe intervention, so they wanted to have more patients undergo the intervention. So the allocation ratio was decided to be 3 versus 1. So 15 intervention versus 5 control patients there. The sample size is set. And also most often we set the power to be 80%, and we will reveal what power really means there. So with all this set up, then the question at the design stage that was asked is what level of outcome difference between the intervention and control group that we can expect after we run the study there. So in this case, the target that I was calculating is the minimum detectable effect size. In another way to say is what is the level of difference of macular pigment density between the two groups that likely we can detect as statistically significant after we run the trial with 20 patients there. So this is another thing that I calculated using the PSS calculation, this tool there. And now moving to another third example, which is a more recent collaboration there. And it is not the original scientific question there. I adapted that for the teaching purpose here, but this is an example on monkeys, crab eating macaques there. Now, this scientific question I specify here is trying to use the monkeys to see whether there's some relationship between a certain kind of retinal marker and diabetes there. So the retinal marker, you can understand that as, but all these monkeys have OCT images there, and there's some kind of retinal marker can be derived from the images there. So the scientific question is to study relationship between retinal, this phenotype, with diabetes in these monkeys there. The sample size, yes, and this image actually comes from Dr. Das' lab there. So thank you for allowing me to use the OCT image here. Now, in this context, there's this just one animal lab there. They just have over this 300 macaque, the monkeys there under observation, and they have obtained, amazingly, they have obtained all the OCT images there. So in this context, if, for example, I assume that a relative risk of 2, meaning that the monkeys with this retinal phenotype have a double risk of developing diabetes compared to the monkeys that do not have the phenotype. I consider this as something clinically or scientifically relevant there. Then the question I can answer that what would be the chance of concluding that this relative risk of 2 will be also statistically significant there. So this is another kind of question I could answer, and I could use power and sample size calculation to answer the question there. Summarizing all these 3 examples, what we are trying to see here is in the first example, the fishing village HIV prevention there, I was trying to calculate a sample size there. The second example, the clinical trial on albinism patients there, I was trying to calculate the minimum detectable effect size conditioning on the sample size being fixed there. And the third example we just talked about, we were trying to calculate the chance, which actually turned out to be the statistical power there. So all these 3 concepts here, these are actually interrelated, and we are going to see that later, okay? And specifically, which specific aspect you want to calculate, that is driven by your specific scientific context or question there. But altogether, regardless what you're trying to calculate, this all belongs to the statistical framework called the power and sample size calculation, okay? So when you see grant proposals, it may say power calculation, but it doesn't mean that you have to just calculate power there. You can interchangeably, all these things can be considered there. So this is, yeah, and here we just talk about one way we may need to use power and sample size calculation to do something there, and why we would need to use that. I mean, certainly that's why you are all here today. That's clearly especially at the study design stage, we do need to know if we run a study, we want to know how big the study needs to be run there. This is not a problem for human study. You always have to have a sample size justification, but can be a problem or under-recognized in the basic science research communities there. I've seen proposals where they're trying to do some experiments there, and they just say we're going to use test on 40, say, mice and 16 rabbits there. And the question immediately arises why you need to use 40 and mice or 16 rabbits. Can you use 12 rabbits there? So in that case, actually, I mean, me personally think for basic or animal studies, it's actually more important or equally important to do sample size calculation to rigorously design your study, because the animals are sacrificing their lives for us to get their data. So we really want to use their data very efficiently there. And similarly, if you are estimating detectable effect size and the number you calculate using the PSS tool there, it can give you a sense what is the result that you might expect after you run a study there, and you can discuss whether that level of difference is something meaningful there. Similarly, statistical power is also if, for example, you have a new drug, you want to test a new drug, if the new drug really works, I mean, you want to have a reasonable chance to detect it, right? And that's related to the concept of power or the probability of detecting a real difference. And we'll go through that later. So with this, what we just talked about, hopefully you can see when you may need to run a PSS calculation there and why you will need to use that. And it's a good habit to build into any of your study design there. And now we're going to move to talk about how to do a PSS calculation there. And before that, any question? I mean, I tend to speak very fast, so feel free to stop me at any time there, okay? And including people on the Zoom there. Okay, so far so good. So now we're going to talk about how to do a power and sample size calculation there. Now this is a big question, of course, and it can get very complicated if you have a pretty complex study or a complex data structure there. And what we're going to do here is using the simplest case of one-sample mean problem. We go through all the statistical considerations behind this, then to do the calculation. So, but this is a simple example, but the idea is all the concepts that we're going to go through will be generally applying to, in general, statistics and power and sample size calculation there, okay? All right, so let's look at this toy example. The context is in a developing country, say China here. The historical data suggests the mean serum total cholesterol level in the male population in a certain region in China was 5.5 unit 10 years ago. So this is the background information. And now public health consideration is that in the past 10 years, there has been major economic development in the region and very heavy influence of Western food there. So now the scientific question is whether there has been a significant increase in cholesterol level in the male population there. And this is a simple question, but it could have high real public health question of public health significance there, as we all know that high cholesterol level is associated with higher burden of chronic disease there. So for example, if this is a real public health question, if a significant higher cholesterol level is detected in the male population, then from a public health perspective, you can do intervention to address the problem there. But anyway, so coming back here, this is our scientific question. Now our goal is to answer the question. How would you answer the question? This is just like everybody's research there. You have a question and you have to think how to answer that. In this case, clearly we need to collect some data, run a study, collect data on a representative sample of men there. And then we look at we measure their cholesterol level values and then to somehow analyze the data to address the scientific question. Before we get to that step, of course, we need to decide how many men we need to enroll to draw their blood to get a cholesterol level there. So this will require a power and sample size calculation there. Before we do a power and sample size calculation, the first step is always to translate your scientific question into a corresponding statistical question. Okay, so you have to use the statistical language to formulate the question so that later you can plug in all the statistical terms there. So in this case, with this question, what we need to consider to do the translation process is that what we're trying to study, what is your scientific interest, which is cholesterol level. So that means our random variable of interest is cholesterol level. And also statistically, what is the type or the feature of this random variable? Is it continuous or categorical or count variable like 1, 2, 3 there? And in this case, cholesterol level, clearly that's a continuous variable there, right? And in addition, what we also need to consider that if you have already collected data, then how would you analyze the data? How would you analyze the cholesterol level? So what is going to be the statistical method you will be using if your data are already collected? So all this information from a statistical perspective need to be considered, and then you can go further to use relevant statistical tool to answer the question, okay? So now in this case, back to this toy example where we just have this one sample, just this group of men there, and we want to look at their cholesterol level change there. So this essentially is a one sample mean problem. This is a tool, a statistical tool called, or more well-known, and you'll probably have heard, this is just the one sample t-test. So one sample t-test is a statistical method that we're going to use if data are already collected. And that's also going to be related to sample size calculation later. Before we go there, first, let's review the statistics behind a one sample t-test there. So here in general, the setup for a one sample t-test, the method, how that's run. The purpose, again, the statistical purpose is to test a population mean there. And in this case, the cholesterol level example, we are testing a mean of the cholesterol level, that variable there. The t-test, whenever when you talk about a test, statistical test, it's always related to hypothesis testing. Here, it's statistical hypothesis testing, which you always have to specify a pair of hypotheses, the null hypothesis and the alternative hypothesis. And in this one sample t-test example, the null is just, the mean is a pre-specified value of interest there, like the cholesterol 5.5, which was the background value. And the alternative hypothesis is the mean, it's a different value there. So the alternative hypothesis is here, this is the two-sided alternative, or you can also specify one-sided alternative. This will depend on your scientific question there, okay? So this is a general setup of the hypothesis behind a t-test there. Now, to do one sample t-test there, we are going to need to, assume that you already observed data, then how are you going to do the t-test? We will need to estimate certain parameters after you observe the data. One parameter very useful and very straightforward, since our focus is the population mean, then of course we can just use the sample mean to approximately estimate the population mean there. So in the notation here is X bar in statistics normally. So here, like say we have N men and we have their cholesterol level, say just say 100 men. We have 100 cholesterol levels collected, and the sample average will be just the average of the 100 numbers there. And you can, and this statistically we know it's a good estimate of the population mean there. On the other hand, the sample mean is only an estimation of the population mean. The population mean mu is not null, okay? This is something you want to estimate. You use this 100 man, this is your study, you use that to estimate that. But this estimation, actually there is still uncertainty in when estimating the true mean there. This uncertainty is because of, or the variability is because of, or statistically, this is really the term, the standard error of the mean there. You have seen, you must have heard of this term there. So what this term uncertainty is, why there is this uncertainty? One is because just in the population, cholesterol levels of men, definitely they're different from each other. So there is this variability itself on this outcome measure of this outcome measure of cholesterol level there. And in addition, when you estimate, when you run a sample with a certain sample size there, you are collecting this specific, hopefully random sample there, then the uncertainty will also be determined by the sample size. And this is the standard error there. You can see that it's determined by both the variability of the variable itself, that's a feature of cholesterol level itself, and also by your sample size. Meaning that the larger you run a study, then you can more precisely estimate your population mean there. Or equally, that means a smaller standard error there, okay? So these two aspects, sample mean and a standard error, these are the numbers that you can, or the statistic that you can estimate if you have already collected data. And yeah, please.
We related the sigma, which is the population standard deviation, to the sample standard error. So are those like, should it be like the standard deviation for the sample for studying?
The standard deviation here, the question is, I know the question, but how do I phrase it? I'm trying to repeat it to the people on Zoom there. They may not be able to hear that. So the question is how the standard deviation
estimate of the population. So here we count it as estimate of population, a standard deviation, not the sample.
Yes, excellent point. Yes, excellent point. So the question is here, this is talking about the population standard deviation, but how about the sample there? So this is a great point in that the population standard deviation, this is more like a philosophical concept that we know there is this variability standard deviation of cholesterol level in the population itself. But this itself is unknown since you don't have all the data of the population. So in reality, we can also estimate this parameter. We're not estimating the mean, but estimating the population standard deviation there, also using the sample there. So yes, this we can estimate that the formula is blocked by this, you can kind of see there is a formula. The S is actually using the sample data to estimate the population standard deviation. Yeah. Okay, so now if we move on, that we review the setup, the statistical setup for a one sample t-test there. Then let's see how we can do the t-test. And we need to go through this because this is where later Poisson sample size calculation come from, okay? So now going back to our toy example and to this one sample t-test, if we explicitly specify the statistical hypothesis behind that toy example, the null hypothesis, then the population mean cholesterol level is still the same, like 10 years ago. The alternative hypothesis is nowadays, the mean cholesterol level has increased. I'm not specifying how much increase, it's just increased, one-sided alternative. And why this is one-sided? Purely because of the way the scientific question, whether there was an increase there. So now we're going to do statistical hypothesis testing to answer the question whether there's an increase. And before we go to the next slide to look at the formal steps, statistical steps to do hypothesis testing, let's use this chart or table to see what statistical hypothesis testing is doing there. Basically, the statistical hypothesis testing is that after you collect the data, you are going to use the data to make a decision about the population truth that you specify in the pair of hypotheses there. So here the column represent the truth. In the population level, it could be the cholesterol level, there's no change. So that's the null hypothesis true. Or population level that indeed there has been a significant change there. Now, the population truth, this is really a philosophical concept there. It's there, but we don't really know what is the truth there. So what we can do is run the study, get the data, and make a decision. And your decision is either reject the null hypothesis or not reject the null hypothesis. So if you compare your decision outcome versus the truth there, then there are 4 possibilities there. The black squares are, of course, these are the good cases where you are making correct decisions. Like here, if there has been a significant increase in cholesterol level, then you are making the right decision that yes, you claim yes, and then you can later do public health intervention there. So this is good. Similarly, I mean, if there's no increase of cholesterol level or say in a clinical trial there, if the drug does not work, then you are not saying it's work. So this is also correct decision there. But on the other hand, if say still the truth is not hypothesis, the drug is not working, but you are saying it's working, that is a serious error there. So that statistically is called type 1 error, okay? Type 1 error, again, is if population truth is the null hypothesis, but your decision is erroneously reject the null hypothesis. That is the type 1 error there. Normally, it's using alpha to denote the type 1 error rate. And then along the same line, if the population level truth is the alternative, say the drug really works there, but you're after you run the study, your decision is saying you cannot say the drug works. That's bad, right? That's also a mistake. That's called type 2 error. So again, type 2 error is that the definition is if the truth is alternative is true, but you are now rejecting the null there. You are now saying alternative is true there. This is called type 2 error. And statistically, the term is the type 2 error rate is denoted by beta there. So now using this chart, then we basically has already summarized what we are statistically hypothesis testing, what we are doing there. Now let's look at the formal statistical steps there, how we do hypothesis testing. The testing procedure, the first step is always we assume the null hypothesis is true. And then we calculate some statistic that can tell us how far the sample is from the null hypothesis there. So this step, the general steps here are true for whatever hypothesis testing problem. Okay, it's not just for this toy example here. What is the toy example? The specific here is the T statistic. So the statistic, what you use to quantify how far your sample from the mean, from the null hypothesis, that depends on your specific statistical method there. So in this case, it's the t-test. This t-test statistic can be calculated by comparing the sample average, right? The sample average is very straightforward to estimate the population mean under the null there. And then the denominator, we have to standardize this distance measure by the uncertainty, the standard error that we mentioned earlier. So clearly, if you look at the t-statistic, that's very intuitively, it is quantifying how far your observed data is from the null hypothesis there. So now think about the t-statistic. That if you run a study of say 100 men and you calculate the t is very, very large, from very, very different from zero there, say, just t very, very large there. If you observe a very large t, would you be more likely to reject the null hypothesis or not reject the null hypothesis there? If your t, the distance of your sample from null hypothesis is calculated to be very, very large there. What does that mean? That means the data are far from the null hypothesis, right? Then in this case, of course, the intuition that we're going to reject the null hypothesis. That's exactly the idea of the hypothesis testing here, where you exactly how far your sample is from the null hypothesis, you can decide on some kind of cutoff. If this cutoff critical value, if your observed distance, the t-statistic is larger than the cutoff that you choose, then you reject the null hypothesis, meaning that your observed data is just too far from the null. So unlikely the null hypothesis is true there. So that's the logic there. And on the other hand, if it's not reaching to the cutoff, then you cannot reject the null hypothesis there. Now the question then boils down to how you can decide on an appropriate critical value. So this often, the critical value is determined by controlling the type 1 error rate to be pre-specified level alpha there. And often, most often is 5%, 0.05 there. Everybody has seen that. So how do we, based on the alpha value, get the specific critical value there? This is where we will need to use the statistical property of the t-statistic that we just talked about. So based on certain statistical theory there, we know that the t-statistic, that distance measure we just mentioned earlier, follows a standard normal distribution as you can see here. So the x-axis is the t-statistic. For example, when you run a study, you are going to be able to estimate the specific t, that test statistic for your sample there. For example, it could be here, you run a test there. The theoretical distribution of this t statistic is governed by the normal distribution, the density curve there, the bell shape. The good thing about putting it into a probability distribution, a known probability distribution, is that then we can use the probability distribution property to connect the type 1 error and the critical value there. Now we just talk about the critical value, the type 1 error, the probability of this is the probability under this normal density curve there. We want to find the t statistic, that critical value, that threshold, where the area under the curve, which is also the probability there, that's right 5%. And we can get this critical value by using the normal density curve. So that's like a calculation operation there. And that indeed is known as 1.64. So the critical value in this one sample t-test case will be 1.64 there. You compare your observed t-statistic to that 1.64. That is the 5th percentile of a normal standard normal distribution. Now, if in the case it's a two-sided alternative, then the similar idea, but the critical value is based on the two-sided 5th percentile of a normal, and because normal is symmetric, so on one side, on each side, that will be the 2.5th percentile of a normal distribution. That number is 1.96. I'm sure you have seen that 1.96, the magic number there. So now we have basically finished about the hypothesis testing, how you do a hypothesis testing by comparing your t-statistic to this critical value there. But you may say that this is not how you would do it. Most often you just say that p-value is less than 0.05, then you will reject the null hypothesis. So that actually is the same thing as looking at the critical value, because the p-value, what will be the p-value? The p-value is your observed t statistic. For example, if you observe your t, the distance measure of your sample compared to the null is somewhere here. Yeah, you can see that here, right? Somewhere here. Then the p-value is actually the probability under the null density curve here that you observe what you observe right here, or even larger than what you observe there. So even further away from the null hypothesis there. So the p-value is the probability of observing t, what your data calculated t there, or even more extreme if the null hypothesis is true there, because this probability is determined by the density distribution under the null hypothesis. So that is the p-value there. And clearly, if p-value is less than alpha 0.05 there, your t will be greater than the critical value there. So using p-value less than 0.05 is the same as saying if your t is greater than critical value, you reject the null hypothesis. It's the same thing there, okay? The other thing to mention is we just talk about the definition of p-value. This actually can be even within the statistical field, that there could be misunderstanding there, but hopefully by presenting that here, this recap helps you recap on the correct understanding. It shouldn't be understood as the probability of null hypothesis true. That's not right. It is assuming null hypothesis true. Then what is the probability of observing what you observe there? And so far, what we have talked about, basically, we have already finished the hypothesis testing problem. But you can see the steps that we took to get the p-value that has nothing to do with the alternative hypothesis. We start by assuming null hypothesis true there, and we're controlling the type 1 error, but that's it. We make the decision there. We're not really touching on what if the alternative hypothesis is true. So now this is related to the power that we're going to talk about later. But here I want to emphasize 2 points there. One is that because hypothesis testing, as you can see, the p-value, how you calculate that is only controlling type 1 error to be less, to be alpha like 5% there. That means that after you run the study, then you have what you have. If in reality, say it's a drug, your drug really works, but you did not, your data are not big enough, or you didn't plan your study very well, after you get the data, then you cannot change the chance you claim the drug will work there, okay? So after you run the study, there's no chance you change the chance of your detecting alternative hypothesis anymore. That's why power and subset calculation, we'll see later, again, it's something that you really have to pre-think at the design stage. That's one thing. The other point about p-value I want to make is that we all see p-values very, very often there. And whenever you see a p-value, it's always from a statistical hypothesis testing problem there. So that means whenever you see a p-value there, when you're talking about a p-value there, there's always a hypothesis, statistical hypothesis behind that p-value. And you should, even though it may not say in the paper what that is, but in your mind, you should be able to know what is the hypothesis that's being tested behind the p-value that you are using to conclude results there, okay? All right, so now we talk about the hypothesis testing steps, then now let's go to talk about alternative hypothesis and power there. So in that case, we've seen this is a null hypothesis, the t statistic has a known distribution there. And indeed, if the alternative hypothesis is true, then the t statistic also has a theoretical distribution. And in this case, it still has a normal distribution for this one sample problem there. The distribution shape is the same, but the difference is the mean has shifted to the alternative hypothesis there. So now if this is the truth, if t follows if the alternative is true, then t should follow this curve, meaning that if we look at the area under the curve, remember our decision earlier hypothesis testing, we were looking at the critical value here. And if the t is greater than z, we will reject that, right? And this is rejecting null hypothesis, meaning claiming that the alternative is true. And this indeed is the right decision under this curve. So the right decision, making that right decision, if it is truly alternative there, the probability is governed by this curve here, the area under this normal probability here. This is indeed the power. So the power is, if your alternative hypothesis is true, then what is the chance that you reject the null hypothesis, claiming the alternative is true there? So you are making the right decision there. And the other direction under the alternative curve is that you made the decision earlier by comparing to the critical value, but your decision was that you couldn't reject the null hypothesis. You are now saying the alternative is true. So this will be a mistake under the alternative curve here. That mistake, the area under the curve, that's actually the type 2 error rate. Remember, it's type 2 error there. So clearly, the probability, under a density curve is 100%. Either you are making a mistake, type 2 error, or you are doing the right decision there. So type 2 error and plus power is 100%, or power is 1 minus type 2 error, beta there. So that's the definition of power and type 2 error. It's the probability if the alternative hypothesis is true there. Now we can start looking at the formula to calculate the power there. Now, going back here, power is really the probability answer under the normal curve, and the normal distribution, the good thing is it's all known, the probability there. So we can write out the power as the probability, and if you move things around, and again, this is conditioning the alternative, the mean is the alternative mean there. Then the power is this probability where you are looking at this this quartile on the standard normal distribution, the axis there. So this can be calculated if you have a normal distribution table there. A few points to comment about calculating power. And from this formula, actually, you can see the elements that will impact on your study power. First, if we look at the numerator here, this part, mu naught and mu 1, this is the distance between your null hypothesis and the alternative hypothesis here. And in this case, it's the two means. One, the null hypothesis mean cholesterol level 5.5 versus the current cholesterol level mean there. So this actually, the distance actually will impact on the resulting probability, the resulting power there. So this is this point, the how separate between the null and alternative hypothesis. The more separate, the larger power. And this actually can be illustrated using the curves that we were looking at earlier. I skipped here. If, for example, this is the distance, your null hypothesis is 5.5, my alternative hypothesis is 6, then this is the power I will have here. But now, if my alternative hypothesis is more than 6, say 7, so even more to the right there, and clearly you can see the decision is now changed because the decision is determined by the null curve there. But now, because it's further away, the area under the alternative curve is much larger. So that means power is larger. You have a higher chance to detect a difference if the difference is indeed very big there. And that's reflected in the formula as well as we just mentioned earlier. Another thing that impacts on some power here is the sample size. Look, the formula here has the sample size in that. So this is actually the larger the sample size, you have larger power there. That's why you have heard of that do not overpower your study, because if you run a very, very large study, like nowadays, big data, electronic health record, I mean, with thousands of records, most often you are going to have over 100%, you can over. You are going to have 100% to detect whatever difference there, even though that difference may not be clinical meaningful there. So you want to be careful not to overpower the study there. Another thing that impacts on the power is the alpha. Remember, the critical value, the decision region is determined by the type 1 error alpha there. Most often, this most often alpha is just pre-specified as like 5%, but I've seen like 1% or 10% there. That's depending on the purpose there. Another thing is to mention is look at the formula here, the sigma. So this is the standard deviation of that variable, like cholesterol level there. This standard deviation will also impact on the power there. In another way, saying that if you have a more homogeneous group, more homogeneous meaning smaller variability of people's cholesterol level, there's smaller standard deviation, then you are going to have a larger power. So you may consider this in your study design there. But of course, if you have a more homogeneous group, you also lose certain generalizability. So it's a two-sided sword that you need to consider. But anyway, statistically, the smaller standard deviation, the larger the power there. Now, another thing I want to go back to mention the relationship between alpha and power there. The alpha, remember, is type 1 arrow there. If you look at type 1 arrow here, this is a type 1 arrow which determines the critical value, so 5% there, right? And then the power will be as shown here. So you can see if you have a different alpha there, like if you choose another like 1% of type 1 arrow, so the critical value will be here because 1% will be a very, very little area under the null hypothesis curve here. So that critical value will be somewhere here. Then the power will be much less than if you are using the larger type 1 arrow there. So the point is that power is also related to type 1 arrow alpha significant level that you use there, which makes sense. I mean, type 1 arrow, if you want to reduce type 1 arrow, then you are actually increasing type 2 arrow there. So all these are interrelated concepts there. Okay, so we just talked about the power formula and how the different elements are impacting on power. And this is a plot that the cholesterol level plot that can shows graphically the different elements, how they impact on power there. So what is here, the x-axis is sample size and the y-axis is power. The green curve is specifying or assuming the standard deviation of cholesterol level was 1.8. So if you just look at this green curve for now, and the mean, the null was pre-specified 5.5, the alternative here is specified as 6. So the population level has increased to a 6 cholesterol level there. So we can see clearly if a smaller sample size, only 25 men there, then I will only have about, say, 39% of power to detect a population increase of cholesterol level to 6 there. But if I increase sample size to 100 men, then my power of detecting this alternative increase of cholesterol level will be increased to about, say, 85, about 90% power there. So the larger the sample size, the larger power. Now, if we look at fixing the sample size, but look at this green curve, which is assuming standard deviation 1.8, and also compare to assuming the population standard deviation 1.4 there. So the larger the standard deviation, the power is only 50% with 40 men, but the power will be about 70% with the same sample size, but if the standard deviation was smaller there, okay? So you can see the smaller the standard deviation, the greater the power, the more likely you are going to detect a real difference there. Now we can talk about, oh yeah, another thing is the formula that we just looked at was based on one-sided alternative there. And we can also look at the formula for two-sided alternative hypothesis there. And it's pretty similar to earlier formula. We're looking at the probability using the normal density curve there. It's just here the Z, this is the normal percentile there. It's using the two-sided alpha percentile. So this will be at one side, it will be 2.5 normal percentile there. So that's the only difference. But clearly it will have an impact on the actual power there. This is comparing that if you have the same problem, the same setup, but if you specify a two-sided alternative versus a one-sided alternative, what the power will look like. The x-axis again is sample size and the y is power. If we look at this setup, which is sample size 55 man there, and the standard deviation assumed to be 1.4. If you specify a two-sided alternative, then I would have about, say, like 75% of power to detect a population increase of cholesterol to 6 there. But in contrast, if you specified a one-sided alternative hypothesis there, then with a sample size the same, 55 here, and again, standard deviation assumed still 1.4, but now the power is increased to be about 85%. So whether how you specify the alternative hypothesis that impacts on your power calculation, meaning that you in your proposal or study design stage, you have to explicitly state whether it's two-sided versus one-sided there. Like you have heard of superiority trial versus non-inferiority trial. They are actually different things there. The alternative is different. The power calculation will be different there. Okay, so we talk about calculating power. Now let's look at how to calculate sample size there. They're all interrelated. So essentially we're using the same formula and we just move things around to now more explicitly calculate N there. So remember earlier power was that probability, but now using the same formula, we now here is just explicitly write out N as a function of the other elements there. So here alpha is still having effect there because it's the same formula. So Z alpha, this is the normal percentile depending on the type 1 arrow significance level there. And then beta is our type 2 arrow or 1 minus power there. So if power most often is 80%, then this will be the 20th percentile of a normal distribution. And then we still have the sigma, then population standard deviation, and then the distance between the alternative and the null hypothesis there. So this is the formula for calculating N there. And then two-sided test is the same idea, just here the percentile is different there. So that's how you calculate N. And we can also look at how we can calculate minimum detectable difference or minimum detectable effect size. Again, it's the same formula as we were using for that power there. We just now move things around to explicitly write out the distance, D, the distance between the alternative and the null there, which can be written out as the other elements, the significant level. Significant level is also type 1 arrow, the same thing, alpha there, and as a function of power, or this is a type 2 arrow, the percentile there, and then standard deviation sample size there. So all these, again, the three things, sample size, power, minimum detectable effect size, these are all interrelated concepts. If you want to calculate one thing, then you need to specify the other elements there, okay? And which target you estimate or calculate is purely based on your own scientific context there. Another thing to mention here is why this is called minimum detectable difference there. This can be a confusing concept there. And this is called the minimum detectable difference because this is the smallest difference between the null and alternative that you can detect with this level of power and this sample size there. Now, we can use this curve to illustrate this idea. If this is the minimum detectable difference, so this is the distance between the null and the alternative, say this is 5.5, the null cholesterol level, and alternative is 6, so the MDD is 0.5 in cholesterol level increase there. Now, in this case, if this is MDD, then the power, say it's 80%. If the actual distance between the increase in cholesterol level is actually larger than 0.5, what we just saw there. So the distance of the alternative cholesterol level is further away from the null, then you can see you will actually have a higher chance, larger power to detect that difference, meaning that you will have a even more significant p-value there. In another way, saying that if you in reality, if the population increase in cholesterol level is less than the MDD, the minimum detectable ones, like it will be somewhere here, like H1, will be somewhere here, say less or closer to the null hypothesis, then you can imagine the curve of the alternative will be shifted to the left, and then your power will be smaller than the original specified 80% there. So that is why, given the power and sample size, you have a minimum detectable. This is the smallest effect size that you can detect, or saying the smallest effect size, you are still going to have a p-value less than 0.05 with this certain 80% of power there. So that's the concept of minimum detectable difference. I mean, you can think a little bit more. It's a little bit, it can be a little bit tricky there. All right, so we talk about all these concepts in power ensemble calculation. Now let's go back to this toy example to answer the scientific question, whether has been a significant increase. So now it's at the design stage. I need to decide on sample size. In order to do that, we need to specify what will be considered a clinically significant increase there. So this is a clinical or medically or public health question, like say, if cholesterol level, population level increase to 6, then that will be some alert for the public health officials. And so I'm here specifying my mu1 under the alternative hypothesis will be 6 there. And also based on historical data, I can assume my population standard deviation of cholesterol level is 1.4 or up to 1.8 there, say. Then with this parameter specified and 80% power and 5% of type 1 error, then how many men I need to randomly sample there. So the sample size can be calculated using the formula that we saw earlier. If you just plug in the elements that we just specified there. So if the power desired is 90%, then the sample size needed will be 67 men there. If power is 80%, then we will need 49 men there. So this is a very simple example, but and then when you present power sample size results there, for you to rate power sample size results there, most often you run a range of different parameters there, since nothing is accurate there. Like power, you can try different level there. 80% is for later phase trial. I mean, definitely you don't want to run the study with 80%, or you don't want to run a study with a power less than 80% there. And then standard deviation, this is itself is an assumption. So you can run a reasonable range there, and you can present it in a table or as shown in the plot there. So this is, hopefully with this toy example, simply is a statistical question, one sample t-test case, we see how to do a power and sample size calculation problem there, and also the really as a review of statistical hypothesis testing, what is that about, what is p-value, and then all the related definitions there. So now to summarize about power and sample size calculation there, how you would do that. The first thing, I mean, it's not actually just power and sample size calculation. Whenever you have data, you need to use statistics to answer a question. You always have to translate your scientific question into the statistical language there, into the statistical question there. And the things you need to consider, like when doing power and sample size calculation, include what are your variables there. So you have the scientific things you are interested, what are the corresponding random variables there? And what are the types of the variables, continuous, categorical there? They will determine different statistical methods there. And also here, we also need to know, have an idea of the method that you're going to use to analyze the data later. And all these need to be considered before you are able to really do the power and sample size calculation itself. And as mentioned earlier, power sample size, as you can see, the calculation is never accurate. It's just a rough idea there. It needs to put in a lot of parameters, and these parameters most often are based on assumptions, like my assumption earlier about standard deviation of cholesterol level there. That is based on like literature review or some pilot data. At least you get a sense of the magnitude of the standard deviation there or other relevant parameters there. That's why if you come for us to do power and sample size calculation, I will ask you to provide certain background parameter or information there, okay? And as a practice, I mentioned already, it's good to calculate a range of plausible values and then see how the sample size is impacted there. And another thing to point out that power and sample size calculation certainly is a statistical thing there, and it's an essential element in study design there, but that's not the only thing. Clearly, study design there has a lot of things, other things to consider. So statistics always has to be considered together with the real context. And here, power and sample size calculation problem also needs to be considered with available resources, like how much money you have, and that's critical there clearly, and enrollment feasibility and how practical you run the study in certain time frame there. All these are relevant considerations during study design, and statistics never is an isolated thing there, not just for designing study, but also for analyzing study there. And another thing to mention is power and sample size calculation. It's not just for designing a prospective study to calculate sample size and then you go to collect the data. Power and sample size calculation can also be used for when you're designing a retrospective chart study, review study, the data are there, or a secondary data analysis study there. In that case, the sample size is fixed there. But remember, you can still calculate for the minimum detectable effect size or the power there. At least that will give you an idea before you put in the effort to run the study, secondary analysis there. It gives you an idea what is the possible level of effect size you may detect after you pay all the effort there. The other thing is, so what is the value of power and sample size calculation? Even though it's not accurate, but we still need it to give us some kind of starting point about the sample size, especially, or the level of power or detectable effect size there. So that's the a very quick basic introduction about power and sample size calculation. And there is this, before we open for questions there, this is actually a very good practice to check on how attentive you were during the past hour there. This is actually a cartoon there. That's very classical cartoon about power and sample size calculation. So I'll see whether I can play it. And then most of you probably have seen that. It's still very fun to watch every time when I see it. Let's watch it and then think about the questions, like how you would do power and sample size calculation there. So
I have a study and I need to know how
let me,
I think I only need 3 pages.
so can people on Zoom hear this?
Yes.
Can you hear this?
Yes.
Anyone
Yes.
text or? Are you good?
Yes.
They can, okay, great. So then I'll play this, and here certainly we can hear this very well.
Okay, what kind of study?
Let me stop, sorry, let me go back to the beginning, okay?
I have a study and I need to know how many patients I need. I think I only need 3 patients.
Okay, what kind of study is it?
I'm doing a lab study. Can I just use 3 patients?
That depends. What are you trying to show?
We always use 3 patients.
Okay, what are you trying to show?
I'm trying to show that drug A and drug B are better than only drug A.
How are you measuring if it is valid?
We are looking at apoptosis. Can we just use 3 patients?
What kind of measure of apoptosis? Do you know how variable the measure is?
We always use 3 patients. That is what we have published before.
3 patients per group or in total?
Yes.
Okay, let's try something different. What type of measure are you using? And is this an in vitro study? An in vivo mouse study?
It is an in vitro study of patient samples, and we are looking at measures of apoptosis after treatment with drug A and drug B versus drug A and control, and drug B alone.
Oh, how many groups are you analyzing altogether then?
My grant is due tomorrow. I just need to know if I can just use 3 patients per group.
Okay, well, you probably should have come to me earlier for help with this.
All I need you to do is tell me that 3 patients are okay.
So, it is not that easy. Your marker for apoptosis may have a large amount of variability associated with it that could make it difficult to ascertain differences based only on 3 patients per group. It also depends on what kind of outcomes you are looking at. Are you looking at normalized changes in expression levels from baseline? 3 patients may not be sufficient to detect differences in these expression levels between the different treatment groups.
I do not understand.
I'm saying that you may need more than 3 patients per group, but that I need more information to determine that.
The serine protease granzyme B is made in cytotoxic lymphocytes where it is inactive due to the low pH of the storage granules. It is measured immediately upon delivery into target cell cytoplasms where the pH is neutral. This is followed by cleavage of bronchus phase 3 by granzyme B in the target cell cytoplasm and the subsequent induction of apoptosis. All proteolytic events can be quantitated at the live single-cell level by flow cytometry and imaged by conical microscopy.
I understand very little of what you just said. Maybe we should talk more about this.
I just need to know if 3 patients are enough. My grant is due tomorrow.
We will need to meet to better understand this before we can determine the appropriate sample size.
I can put you on my grant for 0.5% FTE. You can design and analyze the data later.
Do you really think that is enough to do the work?
Well, it may be less if it is awarded and the budget is cut.
Please go away.
Okay, so that is fun. I've watched many times. It's still fun there. If it's already over 1, so feel free to step out there. And then this is basically finished there. If you do have time to stay, then we can think about just watching that. What was the statistical question that you can translate from their research question and think about what are the variables of their interest there and what statistical method that will be used to analyze the data after if the study was run there. So all these things actually, when you heard about the cartoon there, actually it mentioned the different elements that we just talked about in this talk there. So those are things that you can think about. And with that, I would like to wrap up this seminar. I apologize for it's going over 1 o'clock then. And feel free to stay if you have questions or discussion there. Okay, so thank you for people who are here and for people who are on Zoom there. Thank you. I think I'll stop the recording now. Give me 1 second. How do I stop? Stop share. Where is stop share? Oh yeah, new share. Oh, stop here. This one. Yeah. Thank you. All right. Stop share. No, stop recording. Oh, this was now recorded.
It's on the corner.
Now who's controlling that? Oh yeah, I was. I mean, yeah, okay, I can now stop it. That's okay. We can edit this later. Yes, we will share the slides and the recording will be posted online somewhere. We'll let everybody know there. Thank you everyone for being on Zoom there. And yes, yeah.
Compared to 1 side and 2 side, I saw that when calculations, 1 side and 2 side, the T alpha is 1 side and 2 side are different, but the T beta is the same.
Right. Yes. Yes. Okay, so if we go back to the slides, let's see, we can use those curves to illustrate the idea there. The question is just for people who are still on Zoom there. The question is the question.
So 1 side and 2 side.
Yeah, one-sided versus two-sided alternative. The formula shows beta is the same, but the alpha is one is alpha, the other is alpha over 2 there.
Yeah.
And the And beta is not changed because beta is not related to the critical value. The critical value is only under the null hypothesis there. So that's the so that's nothing about beta is a type 2 error. So that's nothing about to do type 2 error there. If it's one-sided, then we will only look at one-sided here, the tail probability. But if it's two-sided alternative, then we will need to look at the distance of the t versus the null there. The distance in terms of the absolute value. So it could be larger or smaller than the null hypothesis. In that case, we need to consider the tail probability either on the right side or on the left side. So we need to split the 5% of type 1 error to 2 on the 2.5 on each side because normal is symmetric there. So that's why.
The second question is, what's the acceptable for publication normally power? It's about 80% or can be 75%?
Yeah, so the question is, what is the acceptable power in publications or in general doing research there? That's actually a very good question. So there is no golden rule there, but 80% of course is like a rule of thumb there. But in reality, it depends on the stage of the study. If, for example, in clinical trial, if it's an early stage design, an early stage clinical trial, where your focus is not necessarily efficacy, you don't need to have a high power study. At the early stage, the most important is safety. You probably just want to run the study in 3 patients, I'm making this up, in 3 patients just to show at least this treatment is safe there. So in that case, power in terms of efficacy there is even less of a concern there. But other than that, in most often it's like 80%. But for later clinical trial, if it's very feasible and affordable, you do want to give yourself more chance by saying like 90% power there. Yeah.
Yeah, very great. Thank you.
Thank you.
So, Jean, can
any
you,
question here and see whether there's any question?
yeah,
Zoom.
can I ask a question? Can you hear
Okay,
me?
there's no question. Are we good here?
I have a question in general. Do you have like you said that you would share the slides on the JH website? Are there like previously, because this was really helpful,
Mm-hmm.
are there like previously recorded seminars where you would
Yes. You mean this particular slides there? The slides, yes, it is available online through a course there. So you will have to register. You can audit that. That the course is offered in the Square Public Health. So if you check on JHSPH's course catalog, power and sample size calculation for epidemiology studies there. Yeah. Actually, now there are 2 courses, 2 1-credit course each there. There's a number 1, which is the basic there, and then there's a more advanced power and sample size calculation course there. Both are online, pre-recorded. Yeah.
Question. I'm just like a pilot. Like we just want to like use whatever like key value these are there, and whether the number is above or below 0.05.
Yeah.
And then ask other people, like, did you use 1 pair or 2 pair? Like some people, just use 1 pair because that just gives me a better data.
Right. Exactly.
Without knowing it.
Yeah.
So
Yeah.
let's say there are 2 cases. Like there's a one particular job, for instance. We don't know whether which way it will show us, whether it's beneficial or harmful. I mean, that's rarely the case, but just for the sake of discussion, that's the case. So it could either be harmful or it could be like beneficial, like say this. And in that case, I understand we should do 2-tail test.
Two what?
2-tail.
2-tail, 2-sided. Yeah. Okay.
Let's say we established that toxicity, and now we know that this is beneficial. And we just want to know like how good, let's say this was taken in another organ and we want to use the guy. Like we know that there's no harmful event. So we only are interested in whether it's showing like beneficial effect or no beneficial effect.
Mm-hmm.
In that case, is it safe to use a 1-pair?
Yes. So one to use 2-sided versus 1-sided there. The 1-sided there, it is dependent on the well, first one to use ideally. it is something you specify in the protocol state before you run the study. That avoids any ambiguity later there. But in reality, I mean, a lot of analysis is post hoc there. So most of it is two-sided. One-sided, you're right, you have to have some kind of justification there where you really like have some prior knowledge that you really know that it just can't be smaller than that. It has to be larger than, yeah, then that's acceptable there. But the ideal case is really to pre-specify that before you, but we really don't want to do the like p-value fishing, like what you might, yeah. Exactly, right, yeah. Most of them is two-sided there because it's really hard to say that this is really just going to be larger there. Yeah, great. Thank you, everyone. Oh, okay. Thank you. Jay has a question. Thank you. So the question is, how would this analysis change for non-normal data distributions there? T-test assumes data is normal. Do these calculations assume normal data distribution as well? Yeah, that's a good point there. The normal distribution that we use is the T-test statistic. It's not the distribution of the variable itself. So it was not assuming cholesterol level, that variable itself follow normal distribution. So the answer is no, we don't have to assume the variables, original variables, they don't have to follow normal distribution. And we use the whether, yeah, so that answers the question. The T-test, for example, it can be used for non-normal distribution. By non-normal meaning that the data themselves are non-normal there. And in this case, the t-test, the one sample t-test there is, what I'm trying to say. The one sample t-test there is using normal distribution for getting the p-value or the t-statistic follows normal distribution. But this is only specific for this example there, okay? There for other hypothesis testing problem, for example, you might be testing the beta coefficient from a regression model there. There, it's not necessarily using a normal distribution for that, for the test statistic there. It may be using other probability distribution there. But the point is to use some kind of distribution in order to get the probability, the p-value there. And that is all, what distribution to use is really dependent on the knowledge of the statistic theory behind that specific hypothesis testing procedure there. Yeah, I think we're good. Thank you. Yeah, thank you for joining, people joining online there, and thank everyone here for staying. Thank you.